I also wanted to mention that we have all the notes available on Discord for these. So hop in, !Discord, you can hop in the Discord. Or if you're watching on YouTube, the link is in the description. And I put the notes on there beforehand so that if you want to look, oh, am I off? I'm off. That's what I was supposed to do. So if you want to look beforehand, you can go ahead and take a look. There we go. You can go ahead and take a look at that. So you don't have to take your own notes. You can just follow along. Okay. So we are on Lagrange Mechanics. Let's try again. Lagrangian Mechanics, Part 8. Now not last week, the week before. Last week we had off for Christmas. But the week before, we talked about Lagrange multipliers. Constraining forces are usually not included in the Lagrangian formalism, but they can be. Like, you can write the Lagrangian mechanics in a way where all the constraining forces go away nicely. They all cancel away. But in this particular case, there might be an interesting thing that the constraining force could tell us, like tension in a wire, or structural integrity, or something like that. Like that we would want to know what the normal force is, right? Lagrangian mechanics, there's a good way to do it so that stuff goes away naturally. But the constraining forces can be found by using Lagrange multipliers. So you might consider like a constraining function, x of y, which is equal to some constant, right? And for example, and we're going to be using this example tonight too, this is going to be the third time we're solving Atwood's machine. Atwood's machine is a good example of when a Lagrange multiplier can be helpful. Specifically, if you want to find the tension in the string, right? So the function for the Atwood's machine that we were considering was x plus y, which is equal to some constant, right? And we found that if we wanted to consider this constraining force, we could rewrite the equations of motion as the following equations of motion. So we have your normal derivative of the Lagrangian with respect to x plus some lambda with the derivative of this constraining function with respect to x. And this is just for the x direction. It follows the same way for the other directions as well. And then the derivative with respect to time of the derivative of the Lagrangian with respect to x dot, right? So now if we found out that so if we solved these equations like we did last time, and again, this is video, will be on YouTube soon. I just haven't got it up yet. You can find that the lambda in this equation just turned out to be the tension the whole time. So there's certainly a way where we can solve for it and figure it out for that, right? Okay, cool. Now, next up, we're going to be talking about today's topic, which is Hamiltonian Mechanics. And one of the things that somebody asked a long time ago, this was before, like directly before I found out that I had to change advisors and stuff, so I wasn't able to answer it then, but I'm able to answer it now. Someone asked, what was Legendre transformation, right? That was, but yeah, it was what's a Legendre transform and when do we use it? So we're going to get that for free tonight, and that was kind of the point of doing this, is I wanted to show that too. But we're going to talk about Hamiltonian mechanics in general. What are Hamiltonian mechanics? So far in up to this level in physics, if you've gotten to this level in physics, you've learned about Newtonian mechanics, which describes the world, and this is all in the notes. So I'm just pretty much reading off of my own notes. Newtonian mechanics describes the worlds in terms of forces and accelerations. I mean, F equals ma, blah, blah, blah. The potential energy is equal to the derivative of the integral of the force times, ds or whatever. Who cares, right? And then Lagrangian mechanics uses generalized coordinates. Now this is the fun one, so I get excited about this. Uses generalized coordinates to be considerably more flexible. It has advantages of eliminating constraining forces. Or we can introduce them again with Lagrangian multipliers. And but it also has weaknesses when it talks about dissipative forces. Right? So we're going to also find out now with Hamiltonian mechanics that it's flexible just like Lagrange mechanics. It uses Hamiltonian's equations instead of Lagrangian. And we're going to do the Hamiltonian, which we derived the Hamiltonian the week that we did conservation of energy. That kind of comes into play with the conservation of energy material. And we did find out that the Hamiltonian is just the total energy, and it has some sort of physical significance, which is that there's systems in which the energy is conserved. The total energy should be conserved, right? So, and likewise, it's suited to handle other conservation qualities better than other formalisms as well, like momentum and things like that. But we're going to kind of get to the Hamiltonian from the Lagrangian. So let's start that process. So we're going to start with our Lagrangian, the glorious Lagrangian, T minus U, the kinetic energy minus the potential energy. Now, let's see. This led to an equation of motions for the Euler-Lagrange. This was all the way back, like in the very, very beginning, where we have the equations of motion for the Euler-Lagrange equations from the Euler-Lagrange equations. And the Euler-Lagrange equations are the derivative with respect to the L divided by the derivative of Qi, where Qi is the generalized coordinate that we talked about, is equal to the derivative with respect to time of the derivative of the Lagrangian with respect to Qi dot. And these generalized coordinates of I run from 1 to how many ever generalized coordinates you want. For all intensive purposes, we're going to stick with one generalized coordinate for today. Okay? So is this the idea that both Hamiltonian and Lagrange mechanics lead to the same solution? Or are they used for different things? So they can be used for different phenomenological things, but they all derive out of the same thing. So you can get Newtonian mechanics into Lagrangian mechanics and vice versa, and you can do Lagrange mechanics into Hamiltonian vice versa, and then subsequently you can go back and forth between Newtonian and Hamiltonian mechanics and stuff like that. So that is kind of what we do with those. Soon ask, what is dark matter? Soon I'm going to get to that after this. I want to kind of go over this stuff ahead of, and then we'll do questions like that after. If you want to stick around or come back in about maybe half an hour, we'll do that. Or so type. So Tyrion, could you throw that in the queue for me? That would be helpful. And then we'll talk about that. Classically, they are equivalent. There are reasons you might want to use one. So yeah, and so Lagrangian mechanics makes a lot of symmetries more manifest. Absolutely. And so like one of the things that you think about too is Hamiltonian mechanics is kind of set up best for the for quantum mechanics, in my opinion, and Lagrangian is set up best for quantum field theory. Thank you, Tyrion. But yeah, so actually cosmic Gaussian, that's what we're working from. So if you are new here, all of the Lagrange mechanics discussion series that we've done is from chapter 7, except for today. Today's from chapter 13. So that's where this is all coming from, is from John Taylor's chapter 7 and 13, which I think is a phenomenal book. I struggled with it when I took the class, but since I've re-looked into it, spoilers then. Okay. So we can write the equations of motion, and we get the different coordinates, and we can get some generalized, generalized.
Chapter 6, 7, and 13, actually.
Oh, 6, 7, 13. That's true. We started with calculus of variations. I forgot about that. Thank you, Tyrion. So we start with the generalized momentum. Or no, we also have the generalized momentum, I should say. We don't start with that. But we also have the generalized momentum, which we have established several times to be Pi is equal to dl over dqi dot. Now, you can see that, right? Yeah, so that's going to come up kind of frequently because the Hamiltonian, and we saw before, is given by the sum. This is one of the ways to write the Hamiltonian. The sum over all of the Pi qi dots minus the Lagrangian. Now, if you want to see how we derive that, you got to go back and look at the conservation of energy videos. Very, very good stuff. Hey, Slayer. Good to see ya. Welcome, welcome, welcome. So the other thing about the Hamiltonian is we found out to be total energy, right? So we'll get into that soon as well. But there's two formulations of Hamiltonian. There's this one and the formulation of total energy, which, again, we'll need both of those today. So let's consider a Lagrangian system, right? We're going to go back to Lagrange Mechanics for a second. And now we're dealing with, like I said, a Lagrangian system with one generalized coordinate. That's it. We're going to do everything extended to Hamiltonians in one generalized coordinates. And you should be expected to understand that it does translate into many generalized coordinates the same way that the Lagrangian mechanics translated into many coordinates as well. Okay? So let's start with one, and let's write out this very generalized Lagrangian. The Lagrangian is equal to, now it's going to have, we're going to write it in its glory, so Q and Q dot, where Q is just a placeholder for whatever generalized coordinate we have. And we have the kinetic energy, which is a function of Q and Q dot usually. And the potential energy, which is U, which is usually just a function of distance, okay? Oh, nice. Cool, Ash. Okay. Yeah, the exercises in this are very, very good. Very helpful. So let's see. So for example, if we wanted the simple pendulum, so we have the simple pendulum example. Where we have the Lagrangian, and now we have a coordinate of phi and phi dot. So this is the actual coordinate that we did when we solved this, and we had 1/2 ml squared phi dot. But this is a kind of a nice one, right? mgl 1 minus cosine phi. This is kind of a nice Lagrangian, right? Because we had this, because we only have this one generalized coordinate, and this kinetic energy term relies only on phi dot, and the potential energy term only relies on phi. But if we considered a bead sliding on a frictionless wire, then what happens? Well, we ended up getting a different Lagrangian, so let's write that one down. And it's a little bit more complicated. But again, we still have phi and phi dots. We only have the one generalized coordinate. But now our kinetic energy term looks something like this, where we have 1/2 m, 1 plus f prime x squared x dot minus m g f of x. Okay? Where this was where this was the very generalized system to handle that. Let me double check something in my book real quick. Make sure I don't have any typos, as I like to do from time to time. Both check for typos and also make them. Yeah, so it's not a very pretty looking thing, right? We're going to have that same T minus U thing going on with the kinetic energy and the potential energy, but we have all this extra junk in here, namely that this function could depend on x. Okay? Phi dot should be squared. Did I miss that? I did miss that. Good catch. Thank you.
Cosmic Gaussian says phi dot should be squared.
That is a common error of mine, is to miss the squaring of the kinetic energy term. Did I do it again down here? Or is that the way it's supposed to be? I did it again there, too. Look at that. That is a common mistake I make, as I keep forgetting to square my kinetic energy. Okay, now, there is a nicer way to write this, as one can find out with a little bit of manipulation. You can write down the Lagrangian, and it's all the same in the notes, so the notes should all be good. So if you are following along with the notes, those squares are there. But this is a little bit more complicated, like I said, because this f could depend on distance and as well as the velocity. So now we have it a little bit more complicated. But we can rewrite it in kind of a different way, where we think like, t minus u is equal to 1/2, where we have just some function of distance times q dot squared minus u of q. Now we do have this function of distance, so we're not losing anything, right? This function of distance can be whatever we need it to be to satisfy, this equation up here. Whether it's not just m plus, m times 1 plus f prime x squared. Yeah, we did have speak on for everybody cosmic for a while, but then people started to abuse it, so I had to turn it back off. Soon, thank you for the follow, by the way. I don't think I said that earlier. I apologize. Thank you. Let's see. So now, the kinetic energy depends on a sub q, or a of q, I mean, and in some complicated ways we don't really need to consider, or we don't need to know what that complicated is right away. But we can know that it's there, and we have to deal with it at some point. So let's think about the Hamiltonian for one general coordinate. Again, we're going to bring out, this mamma jamma, p q dot minus the Lagrangian. And now our generalized momentum, if we want to think about it, our generalized momentum can be the derivative of the Lagrangian with respect to q dot, which turns out to be a q dot, right? And this is what? Well, this is just telling us that if we have pq dot, so we want to think about what this term is, right? We want this to be a of q dot squared, which turns out to equal 2 times t. So therefore, we can get back to our thing where we have 2t minus the Lagrangian, which is t minus u. So this is just, again, to show us that t plus u exists in this, and that we have, and then we have a, we retrieve the total energy of the Hamiltonian. Okay, good. Now, what's next? Well, we have the total energy. What can we do with it? We have too many variables, right? So we brought back the generalized momentum right here. We're going to be referencing it again, but I should have it over there, so hopefully it's good. What do we do with all this energy? All this total energy? All this total energy inside my trunk. We have too many variables, right? We have p, q, and q dot. And it just seems unnecessary. Can we get rid of one of the variables? Well, absolutely we can, right? So we have too many variables, so let's just solve q I dot to be equal to, actually no I, let's just do q. Q, and then what's this equal to? P over a of q for one variable. Again, it goes on with everyone else. And we can say that this is a function of, a q dot is now a function of p and q, right? A is just a function of q, so of course it just translates nicely into q dot being a function of p and q. You have to mind your p's and q's. Oh, I should do q and p. See, if you don't mind your q's and p's, or p's and q's, you're going to get everything confused. Don't mind your p's and q's so you're not confused. So now for the Hamiltonian, we get, this is a function of q and p, which is p q dot of q and p minus the Lagrange, and we have q as one variable, and the other variable is q dot, which is a function of q and p. Okay? So far, so good. So now, we can get to the Hamiltonian equations of motion. How? Well, let's talk about see how the Hamiltonian changes with respect to the variables. So the change in Hamiltonian with respect to q is equal to, so let's see, we're going to take the derivative with respect to q, and what do we get? Well, we'll get some q from inside here, and some q from inside here, so it's going to look like p, take the derivative of q dot with respect to q, right, because it's a function of q, and then we have minus, and then the derivative of the Lagrangian with respect to q, so the derivative of the whole thing, plus the derivative of the Lagrangian with respect to q dot. Because we're introducing this physicist 1, right? That's what I like to call it. We have q, the dq dot over dq dot, and we're just sort of popping it in there. Adam. That's funny. I like that. So we're going to introduce the physicist 1, where we have dq over dq, and we're just going to insert that. That makes everything look nice. Why does that make everything look nice? Well, because this right here is just the generalized momentum. Okay? Also, the Hamiltonian lives in phase space, and Lagrangian lives in position space. Yep, absolutely. That's another thing that Taylor goes into. I probably won't talk about that too much just because of time. But that's another thing that Taylor goes into that's very, very cool. And also a very good indication as to why Hamiltonian is better for Lagrange or quantum mechanics. So this is so here we have p dq dot dq, and then p dq dot dq, and the signs are different so they're going to go away. So this turns out to just be the derivative of the Lagrangian with respect to q. That seems pretty crazy, but it's true. What if p is a function of q?
Unless you do another lecture on Hamiltonian Mechanics.
P is not a function of q unless q dot is a function of q, right? Is that how that would work? Which q dot is a different variable in this.
Welcome to the channel.
Let me get these high. Bachi, thank you for the follow as well. Ronxian, thank you for the follow. Bachi, if you do have any questions, exclamation mark ask and your question, and I'll handle it as soon as I'm done with the discussion series that we're doing now. But if you guys do have any questions, exclamation mark asking your question. I'd love to answer physics question. Yeah, you show y on the left. Yeah. So it should be a function of q. But they're different variables anyway, so you'd have to rewrite one as a variable of the other, and it would get kind of like, it would kind of defeat the whole purpose of everything. It'd be like trying to take an x equals y function with like an x equals y and z, and then just rewriting it in terms of a different variable. It doesn't, you're not accomplishing anything new, you're just rewriting everything in terms of variables. But good question, Soon. Definitely a good question. Now, what turns it out is that the derivative of the Hamiltonian with respect to q is just the derivative of the Lagrangian with respect to q. So that's awful nice. So what is the derivative of the Lagrangian with respect to q? Well, our Euler-Lagrange equations just say that this is the derivative with respect to time of the derivative of the Lagrangian. Remember, this is our original Euler-Lagrange equation, q dot, which is then equal to the change in oh, I'm sorry, this is a minus. Excuse me. Yeah. Minus the change with respect to time. And this is just, again, generalized momentum. So this is just p. So what does this mean? Negative p dot. So the change with p in the momentum with respect to time. Most fun stream I've been a part of, and no one does this. I'm glad you like it. I love doing it, and I'm glad people enjoy it. Okay, so this is the change with respect to time of the momentum. So this is what? This is the Newtonian force, right? dp dt, right? The Newtonian force. So that shows up right there, black and white. So you can even see bits of Newtonian physics kind of sprinkled throughout nicely. Now, we can do the same thing with the p coordinate, the derivative of the h with respect to p. So if we were to do this, this would kind of kill any of the q's that we were concerned about as well. They show up though. Oh wait, hold on. Oh, I used the eraser. You don't use the eraser. This is going to be q dot plus p dq dot divided by dp minus dl dq dot dp. Where did I get this from again? Again, that physicist 1 entering the physicist, you know, shortcut has entered the match. And this is nice again because here we go again with our momentum, our generalized momentum. So here we go right here. We have this term and this term turn out to be the same thing. And this, in fact, just turns out to be q dot. Nice. Everything cancels away so nicely. It's almost like it was meant to be, right? Now, we are almost done. You guys have made it. This is an interesting thing, though. Let's see this. Okay, so while the Lagrangian is one single second-order differential equations, we now see, because remember the Euler-Lagrange equation that exists right here is a single second-order differential equation. Here we have two first-order differential equations. So this is just dH dq is equal to p dot, which is just dp dt, and this dH dp is equal to dq dt. Okay? No second-order differential equations, so that might be another thing you might find useful in your ventures. I'll look at it later. I don't even know what you clipped. I hope it's good though. But here we have a classic example. Now you guys did this without even realizing. right? Because I never once told you, except the beginning, I said we would be doing it. But what you didn't know is that you just completed a Legendre transformation, right? So a Legendre transformation, and we're going to show this just quickly. The transformation, just kind of like what it means, at least for us physicists. It means a very complicated thing for mathematicians. But for us physicists, we kind of break the rules a little bit, right? So we're going to start with a function. And this could be considered your Lagrangian that has a couple variables. Who cares, right? And let's consider the differential of that function. So we'll have df is going to equal the partial of f with respect to x. And we're going to, you could do it with holding y constant or something like that. Kind of like what we do for the Lagrange, right? We're going to add up all the different pieces of the function dy. Okay, so this is not like crazy, right? This is just what we do when we do the Lagrange mechanics, right? Yeah, same thing with thermodynamic. Yeah, exactly. Same thing with the thermodynamic potentials, definitely. So here we have df dx, df dy. Let's relabel those. We'll call this one u, which is df dx, and w, which is df dy. And now we can relabel df, the differential of f, as u dx plus w dy. But now let's also consider something else, right? Now remember, this is already very well-established stuff, so I may be making jumps in logic, but that's just because somebody else at some point in time did not, right? And now we know a better way of teaching it. So it may seem like a jump in logic, but in reality, at the time that someone was doing this, they had to work this all out. Probably not in this order at all. But let's see, what if we did the derivative of yw, or wy, excuse me. So we did the derivative, this is just a chain rule, right? Or the product rule, more or less, excuse me. Y dw plus w dy. Okay, no big deal, right? Just going to pull that out. Then what happens if we subtract these two equations? Okay? We'll get df minus dwy is equal to u dx minus y dw. Okay? Nothing crazy, nothing crazy. So what I'm going to do is I'm going to say, okay, we'll take this. Okay, we know we have these. These are established. That's nothing crazy. There's nothing weird about that. Now I'm going to say, and the only thing that really changed here is we just took this and flipped it, right? So now it's y dw. I'm going to set this equal to something. I'm just going to say, I'm going to call it dg.
Welcome to
okay?
the channel. Things get a little bit.
So we're going to say dg is equal to df minus dwy. Okay? Viral Corgi, welcome to the channel. Thank you for the follow. Thank you for the update to the schedule, Tyrion. I appreciate that. And I'll go and try to change all of that, too.
Weird.
Assault Slayer, thank you for the follow. Welcome to the channel. Welcome, welcome, welcome. So now we're going to have this differential form of this new thing that I'm defining for g. Just say, okay, it's a g thing. Let's define it, and then let's say, okay, well, what's it look like in its non-differential form? Well, it's just taking the d out, right? We're the magic physicists that get to do this type of stuff. And g is equal to, I'm pretty sure the Legendre Transform is a very well-established math. In fact, I know it's a well-established mathematical thing. So it may seem a little bit physics mysterious, but it's not. And then we get this function g, which equals to f minus wy, which happens to be the same thing we did with the Hamiltonian Lagrangian mechanics, right? We did that same thing with our Hamiltonian is equal to p q dot minus Lagrange, right? So there's the Legendre transformation. It's been right under your eyes. You may or may not have seen it. I sure missed it because afterwards I I looked up how to do the Legendre transformations in Taylor. I wanted to make sure I talked about the Legendre transformation today. I looked it up. I knew that it existed somewhere in this mix, but I didn't know where exactly. And then it pointed me back to the page that I had literally just done all the notes on. And I was like, oh, there's a little footnote at the bottom that says this is the Legendre transform. You just did one. And I was like, that's awesome. So there it is. The Legendre transform is a very powerful mathematical tool. and we use it to get back and forth from Hamiltonian to Lagrangian mechanics. Once you get into the QFT, the Hamiltonian is equal to the negative Lagrangian, I think it is, or something like that. Or it's like minus IL or something ridiculous. It's pretty funny. But don't worry about that. That's just a fun anecdote. So we have one more thing to do, is the Atwood's machine. We have solved it. This will be the third time we solved it. And it's turned out to be one of my favorites. So as a consequence, you all get to watch me solve it again. Ha-ha! Or follow along if you have the notes on Discord, !Discord. So we solved the Hamiltonian equations. Remember, for the Lagrangian, we had the kinetic energy, which was 1/2 m1 plus m2 times x dot squared. And then we have the potential energy, U is equal to minus m1 minus m2 gx. But now consider either form of the Hamiltonian, okay? So remember, I said the Hamiltonian takes on two forms. It's going to either be t plus u or p q dots minus the Lagrangian. Either way, well, let's do this. Let's figure out what the generalized momentum is. Remember, the generalized momentum, p, is going to equal the derivative of the Lagrangian with respect to x dot, which is equal to m1 plus m2, all times x dot. Remember that? We just take the derivative of this. The 2 comes down, cancels the 1/2, and we just get the rest, right? Power rule. Straightforward power rule. Thanks, Terry. And since u does not depend on x dot, then we can solve for x dot and say that x dot is just going to equal p divided by m1 plus m2. Now, if the potential did, we'd have all sorts of conservation problems. But if the potential did depend on x dot, then this would not be true. But it is true for the Atwood's machine. It's time independent though, so you can use sure. So you can or can't? Can? Sure. But I'm just going to do this, and we don't even need to because we can write them both out, and it doesn't matter which one you write out for taking the derivative of. They're both going to be the same way. So then what you need to do is write the equations of motion. So let's rewrite the Hamiltonian. And whichever method you pick will work perfectly fine. We'll get p squared over 2 m1 plus m2 on the denominator, minus m1 minus m2 times gx. Okay, so that's the Hamiltonian. And now the Hamiltonian for the equation motions is just given by following our little subset of rules. X dot is going to equal the derivative of the Hamiltonian with respect to p, and that's just p over m1 plus m2. P dot is going to be the negative derivative of the Hamiltonian with respect to x, and that's just going to be m1 minus m2 times g. Hopefully you guys can see that still. I can read them fine. There it is. You are weird, so you don't count? That's fair? Okay. This is a p dot. So if you want the acceleration, then we can combine them and take the derivative again with respect to time. We get x double dot is going to be equal to p dot over m1 plus m2. I will zoom in on this in a second. And then p dot we know to be m1 minus m2g, so we get m1 minus m2 times g divided by m1 plus m2. This is the solution we always reach when we do x double dot. And we have found this one, like I said, 3 times. Let me zoom in on that last little bit there so you guys get that. There she blows. The beauty. The Atwood's machine solved again. This one's really nice. We just have 2 linear differential equations to solve, and it's just find the Hamiltonian and take the derivative once. And then if you want to find the acceleration, take the derivative again. Oh, boo, that was the camera. What can is this, by the way? Oh, it's not as fancy as yours, but it is nice, and I love it. It's my the Canon Rebel T7. There we go. But I do love this camera. I think I love this camera a lot. But I've been eyeing that Sony camera. Oh, man. That looked good, too. Your Sony camera looked good. Purge Time! Interesting name. Love it. Welcome, welcome. If anybody has any questions about this or anything else, now's a great time to ask, exclamation mark, ask, and then your question. But we're done. Lagrange Mechanics, Part 8. Solving for Hamiltonian Mechanics, seeing where the Legendre Transformation comes in, and then, again, the wonderful Atwood's machine solved a third way. The first way we solved it, we just did Lagrange Mechanics. The second way, we did with Lagrange multiplier to understand the tension term. And then the last way we did with the Hamiltonian Mechanics. So that wraps up our series on Lagrangian Mechanics. Oh, look at that. T7. Fancy with his adding of things. Oh. Melko, did you see the quantum levitation stuff at the beginning? That was wicked fun. I figured you would have liked that. Thank you, Purge Time. I'm glad you enjoyed it.
Welcome to the channel.
Sensation. Wait, ooh, sensational. Sensational spelled weird. Oh, jeez. We won't finish the rest of it. Welcome to the channel. Sensational. I hope you enjoyed it. This is an Savada clip now. Yeah, it was really cool. Now get a haircut. No, we still have questions to answer. Someone asked me what dark matter is. I think that's a great question. Should we talk about that?